I'm Minakshi Kumar. Today we are starting with our session on digital image processing. Before I start, I would ask my team to know if my screen sharing is there. If my screen, people can see my screen. Yes, okay. So we are starting with the digital image processing basic concepts. To start with, I will start with my presentation outline. We would be discussing what is a digital image, what is digital image processing. We will see various components of image processing, and then we will discuss the first component of image processing, which is image pre-processing. Image pre-processing would include the radiometric error and its correction, geometric errors and their correction. So this is a brief outline on today's session. So before going to a digital image, before starting with what is a digital image, I would start with a very famous adage which everyone has heard in different languages, in your own mother language, in mother tongues and all, which is a picture is worth 1,000 words. You know, everyone has heard this adage in their own languages. With what it means? It means that complex and sometimes even multiple ideas can be conveyed by a single still image. Right? And that single still image would convey the meaning more effectively than you are verbally trying to describe some phenomena, some object. Right? Why it is so? Because human beings are very good at deriving information from still images because of our innate visual abilities, you know, of our innate visual and mental abilities. Now, like for example, if we look at the picture, many of us, right, would get the mouth-watering taste of this desert, which I have shown here in pictures. Some of you would even imagine licking the desert or taking a scoop out of it, right? And we don't need so many words to describe this picture, right? We don't need so many words to describe this picture. The picture itself conveys the information what is being offered here. But in our context, we are talking about the remote sensing images, about the analyzing or the pictures which have an overhead perspective, that is our remote sensing data which is looking from top. And we are talking about the radiation which is beyond the visible, right? The things which we cannot see with our eye. So we are trying to analyze those pictures, our remote sensing data. From one image, again here the this saying holds true for the remote sensing data also. From one image, many different scientists extract different information. Many analysts will extract different information. A water resource scientist would extract information related to his application. An agriculture scientist would extract information related to his application. So that means one remote sensing data caters to your multidisciplinaries for analyzing the image. So that is why it holds, this adage holds true for remote sensing data also. Okay. Now, before coming again to digital image, we should know what is an image. An image is a pictorial representation of an object, of a scene, or even a phenomena. A phenomena can be pictorially represented. Right? Like for example, here I am showing the portrait of Mona Lisa, a portrait of a photograph of a girl child with black and white, right? Grayscale image, you can say, a satellite image of our list 2 cents. So what are these? Right? These are images. A portrait also I'm saying is an image. A photograph is also an image, and the satellite image also I'm saying is an image. So for that, we should understand what are the various forms of images. There are two forms of images, analog images and digital images. Now, analog images are the ones which I have displayed here. The portrait is analog, the photograph is analog. This satellite image is also a analog representation of the image which was captured in digital. An analog image, if most of you who are familiar with electronics, you know the difference between the word analog and digital. Analog is a continuously varying quantity, just like our electricity. So here this picture also, if I say this photograph, it's a grayscale image, it's an intensity, right? Objects which are reflecting more energy are brighter. Objects which are, for example, here, the here and all, which are reflecting less energy are darker. So this is the visual representation of that intensity. Okay. So here these are the colors. This is the satellite image false color composite. Right? I hope by now, I hope you understand what is a false color composite. So here also this is displaying intensity, colors, shades. Right? So this is the analog representation of the data which was captured in digital. Now, analog image interpretation was discussed in the last session. Today we have to do digital image processing. So for digital image processing, my image should also be digital. Right? Now, digital image processing will work on digital image. Now, what is a digital image? Digital image is produced by or captured by electro-optical sensors, right? Like those CCD arrays which have been discussed, or the push broom and the whisk broom sensors, mirror sensor detector assembly, and the linear array on the push broom array, right? So those are electro-optical sensors, charge-coupled devices. They capture my digital image. How they capture my digital image must have been discussed in the remote sensing sessions, right? Now here, when the image has been captured by those satellites and transmitted to the ground station and sent to the analyst for processing, we get the digital image. Now, how does it look like? It looks like this, a sequence of numbers. It is basically a sequence of numbers, simple numbers arranged either in a matrix form or a simple linear form which you have to arrange in a matrix. So a digital image corresponding to the ground, you can say, it is made up of tiny equal areas. Like here, it is made up of tiny equal areas which are abbreviated as pixels or pix, picture elements, you know, and they're arranged in a matrix form. They're arranged in a rectangular array. Now, with each pixel is associated a number. With each pixel is associated a number, and this number can be called as digital number or brightness value or gray level, GL. Right? Now, this number is a record of reflected energy, right, which is converted to a digital number, and then it is recorded by the sensor. Now, the concept would be similar to my analog images. An object which reflects more energy in the previous slide had a brighter image. Here, it will have a higher number. Let's say, like for example, here, it will have a higher number. An object reflecting less energy, like for example, here, would be having a low digital number. So, this is the structure of a hypothetical image which I am showing here. Small image, 5 rows and 5 columns. Actual remote sensing data will be very large, huge images depending upon the swath of the satellite, depending upon the spatial resolution of the sensor. You will have number of rows and number of columns. This is only a hypothetical. Now, the size of a pixel would correspond to the spatial resolution of the sensor. The resolutions and all must have been discussed in the previous sessions. So the size of this pixel depends upon the size, spatial resolution, and the range of the values depends upon your radiometric resolution. If it's an 8-bit radiometric image, that means 2 raised to power 8, 256 different quantization levels will be there, 256 different brightness levels will be there. What it means, the range of values will be between 0 to 255. Right? So 0 will be for objects which do not reflect any energy, and 255 will be for objects which reflect total energy. Let's take an example of 10-bit, 2 raised to power 10, 1024. So values will be between 0 to 1023 and so on. Okay. So if this is a digital image, a remote sensing data is multispectral in nature. The previous image can correspond to a panchromatic data where you have only single band. But multispectral remotely sensed data, that means the image for the same area is captured in many spectral ranges. It is captured in many spectral ranges. And here, for example, in band 1, band 2, band 3, band 4. So many spectral ranges. Again, this is the visual representation of the satellite image. This is visual representation of the band 2, and these are the digital numbers which are making up the image in the background. Then you are also familiar with the concept of true color composite and the false color composite. A true color composite can be generated when we capture the data in the blue, green and red spectrum and display them in the blue, green and red of the monitor. Right? So this is true color composite. When you simply change the order, right, that becomes a false color composite. In remote sensing, the standard false color composite means the standard false color composite means the infrared band, the red band, and the green band is displayed on RGB. That is standard false color composite. So this is the standard false color composite for this multispectral, this data set which I have shown here, the list 2 quanta data set for our 4 band separate which I am showing you. Okay, so now we can define what is digital image processing once we have seen what is a digital image. So digital image processing can then be defined as computer manipulation of those digital numbers. Computer manipulation of the digital numbers for 3 main reasons: removing the errors, image enhancement, and feature extraction. So we do the digital image processing for 3 basic reasons: image correction, image enhancement, and information extraction. Now, for the image processing, digital image processing, we require an image processing system. So image processing system would be my simple computer hardware, that is a personal computer. Nowadays, even laptops are powerful enough and PCs are powerful enough to do image processing. But the software that we require is a dedicated image processing software to analyze the digital data. Right? The software that, or if you are a programmer, you can write your own routines. The main task is that my image processing software should provide me these 3 basic functionalities which I mentioned in the definition. That means the image processing software should allow me to remove all the kind of errors. That means correction. It should allow me to do enhancement, right? Which is altering the impact of the image on the. And third is the main thing, which is extracting useful information out of the remote sensing data. These are the 3 main functionalities which any open source software, commercial software, or if you're writing your own code should be able to provide. Right? So then, which are the major dedicated softwares? I have listed few of them. The commercial off-the-shelf training softwares, COTS softwares are like, for example, for training purposes, ZDAS Imagine is used very widely because it's easier to understand. Then there is MV image processing software, IDRISI, ER Mapper, PCR Geometrica, and so on. Yeah, these are some of the commercial softwares which are mentioned here. If you search on the net, you will find a large variety of free and open source software. We have ILVIS, which is Integrated Land and Water Information System. We have optics, GRASS, OSIM, Multispec, CVIP tools, QGIS. If you search on the net, free open source digital image processing softwares, you will get a big list, 10 best image processing softwares and so on. So you will find them in this list, and the list will be long, more than this. Right? So you can, and if you are a computer scientist, if you can program, you can write your own books. Okay, so now coming to, as I mentioned here, my software should provide me, first part is image correction. So now we will see what is the first component, image correction. This is also called as image pre-processing. This is also called as image pre-processing. Now, why this step is necessary? Because remote sensing systems, now by remote sensing systems, I mean the sensors on board the satellite, the sensors on board the satellite, the combination of them, they may not function perfectly all the time. Of course, they are calibrated before being sent to the orbit, right? But sometimes they may go out of calibration and they may not function perfectly all the time. Right? Second is, these satellites and sensors, they are capturing what? They are capturing the Earth surface, right? And there is Earth surface, land, water, you know, these themselves are so complex that you are trying to record them by systems which have limitations. Limitations in the sense, they have certain spatial resolution, spectral resolution, radiometric resolution. So sometimes, not all the times, sometimes error may creep into the data acquisition. That means the imagery which is being captured at one instant. There may be some error which may be encountered, which will degrade the quality of the data that is being captured. And the common type of errors which are encountered generally are called as radiometric error and geometric error. So the correction for the radiometric and geometric errors are termed as pre-processing, because as the name is suggesting, they should be done prior to your information extraction step. Okay. So now there are two types of errors, radiometric errors and geometric errors. Let's see them one by one and their correction mechanism. Now, the radiometric error, radiometry, as you understand, the radiometric resolution, it must have been explained, the quantization level, or you can say in simple words, the DN value, the value that is being reflected by the pixel under consideration and that which is recorded by the sensor. Right? So the DN value, when the value is distorted, it is radiometric error. Radiometry is distorted, it is radiometric error. So what is the reason for radiometric error? The reason for radiometric error is because the data is being captured by the detector. That means the detector may have caused some imbalance. Right? So one reason is detector goes faulty. Second is this atmosphere is there in between. When the sun, the energy is coming to the earth from the sun and it is being reflected and recorded by the sensor, there is atmosphere in between. So atmosphere is encountered twice. Once the energy is coming from sun to the earth and second from earth to the sun. So in both ways, there can be some atmospheric deterioration, some atmospheric error may have been introduced. And they cause, you know, cosmetic effect. The image doesn't look cosmetically good. So these corrections are also called as cosmetic corrections to improve the visual appearance of the image. Now, common radiometric errors are, I will come to them one by one, line or column stripings, line and column dropouts, random pixel stops. Now this was periodic, the complete line stopping, complete line and column dropout or stripings, or it could be partials also, right? And then atmospheric errors. So let's see some of the errors one by one. So first we will start with line dropout. Line dropout name suggests that the detector which is recording the line fails to record. This detector, it malfunctions and it fails to record the entire line of data. Now, this is a kind of a periodic error, because then when the detector fails to record and if it continues in the entire image, it will be a banding pattern. Depending upon the satellite sensor, if there are, like, for example, 16 detectors, so if one detector fails, every 16th line would be a dropout line. A dropout means no value is recorded. No value recorded means zero. Zero means black line, right? So this is called as line dropout. Now this I am showing here complete periodic line dropouts or partial line dropouts, right? Partial line dropouts and non-periodic also, right? This you can also imagine that this can be in vertical direction also. I'm showing your horizontal line dropouts. It could be in the vertical directions. Horizontal direction when in the whisk broom type of sensors, and the column dropouts will be in the push broom sensors when the detector fails to record. Right? So the value will be 0. Now how to correct it? Right? First you have to identify whether the line is a bad line, a zero line or not. Right? Visually it is very easy to say yes, that's the dropout. But how will you use it in the algorithm? So you have to locate the bad line. The simple algorithm would be use a threshold. Right? Calculate the average of each line and calculate the average of the entire scene. A line which has an average of near to 0, that means it's dropped. Right? The value is 0, right? So it is near 0, that means line is dropped. Now, once the line is dropped, how to correct it? Now, one thing please remember, if the line is dropped, if it was never recorded by the satellite, it cannot be, original values cannot be retrieved. So we have to do some arrangement. So we can take the detector in which it has not been dropped. Right? That means if every 16th line is dropped, the 15th detector and the first detector is, if it's not faulty, so you can take the preceding line and the succeeding line. Right? So you can replace the line, bad line, with either the preceding line or the succeeding line, or you can take the average of the two, right? Or you can replace the line with the highly correlated line. So these are the mechanisms for missing lines and columns. Now line striping, it is different from line banding, line dropouts. Line striping and banding are same, but line dropout is different. Now line dropout means these lines would be black, the detector fails to record. But in line striping, the response of the detector shifts towards either a higher value or a lower value, causing the banding pattern. Again, this can be a horizontal banding or a vertical banding. Now, as you can see, it interferes with your visual interpretation, right? Visual appreciation of patterns. So this is a cosmetic defect, and you can see if you compare these two, so the cosmetic banding line has to be removed to interpret the features, right? And this is done using the linear sensor model, right? So variation, because why these come? Because over the period of time, sensor deteriorates. That means its gain and offset varies, right? It has been calibrated with a certain gain and offset. It varies. So we need to fix it by fixing the gain and the offset. We can take a detector which has the true value, that means no error, and the faulty detector can be mapped to the reference detector. So you can build a ideal relationship between the input and output. So input would be your the faulty detector, output would be your reference detector, and you can fit a model between the input and the output and correct your line banding. Now, these are the two type of line dropouts and line banding. I have also written random errors. Random errors would be corrected when you, in the next session, that is image enhancement, using filtering. Now, coming to the second type of errors which can be there in the radiometry is atmospheric induced error. Right? In the atmospheric induced error, these errors are haze, skylight, and sun angle. Let me try to explain you with a picture. Right? Now, what is the ideal requirement? The ideal requirement is, like in remote sensing must have been told to you, there is a source of energy, which is sun, passive remote sensing. The energy is coming from sun and hitting the earth. So suppose if this was the pixel under consideration, so sun's energy is illuminating this pixel. Under ideal relationship, the energy is reflected back and recorded by the sensor. In remote sensing session, you must have been explained these terms also. This is called the energy coming from sun to the earth is called as irradiance, and the energy reflected from the earth reaching the sensor is called as radiance. These terminology, right? So now this is the requirement, direct illumination, right? Energy coming from sun reaching the sensor. But this is not so simple because there is atmosphere in between. And as I was mentioning earlier also, the atmosphere comes twice in between. When the energy is coming from sun to earth and then from earth to the satellite sensor. Right? Now, what is happening in between? In between, the lower wavelengths, as you must have been told, are scattered in the atmosphere. The lower wavelengths, they are scattered in the atmosphere and they also reach the sensor either along with the reflected light or even before it. So the scattered light reaches the sensor and while the sensor is recording DN value for this. So it gets this value plus scattered light. Right? Now this is not so simple that it gets only scattered light. There is another reflection. What happens is, if this is the pixel from which the value is being recorded, there are neighboring pixels also. Right? Now, the sun's energy is reaching the neighboring pixel also. Some energy gets scattered here also, which in turn illuminates this pixel also. So the energy which is coming is not only direct illumination, but the adjacent reflection. The adjacent reflection. So this pixel is also illuminating this pixel. And what is scattered illumination then, or the skylight? Now what is happening? Diffuse skylight. Now the energy is coming from sun reaching this pixel as well as this pixel. Now some energy is scattered in between, and that also goes into the field of view of the sensor. So scattered light which reaches the sensor after being reflected from the sun. That means reflection is here, right? This was coming here, this is reflection, and then it gets scattered, that also is reaching the sun. So you can see it's multiplicative effect. Right? This is multiplicative effect which adds. So this is very complex that the value gets distorted. Second variation in DN value is also due to the sun angle. That means due to different time, due to different season. You know that the energy from sun to the earth, right, changes in different seasons, changes in different time of the day also. So that also is a multiplicative effect. So combinedly, atmosphere is a very complex part which affects the satellite image. So some of the errors which we can remove, simple methods I will tell you. The difficult methods, that means the atmospheric modeling, that is not the that cannot be covered in such short time. Right? Another simple image to show you the different effects. Okay. So this is what effect it has on the image. The first the effect, which I was telling you, the lower wavelengths are scattered. Like for example, the blue light is scattered. It adds itself to the DN value, and the image is hazy, which interferes with the interpretation. And you can see this image is without haze, so you can interpret it better. Similarly here, right? So image with haze have less interpretation. Right? So why their contrast is reduced? Their contrast is reduced. So how to remove haze? Very simple method would be that you take the minimum value in the histogram for that band, right? If my blue wavelength is scattered, I take the minimum value, histogram value, and subtract it from all the DN values in that band. This is a very simple method called as histogram minimum method. The minimum DN value in the histogram is subtracted from all DN values. The second method is that you take the dark object subtraction, where we assume that the infrared band is not affected by haze. In those infrared bands, we identify black bodies. Now, what I mean by black bodies here, objects which do not, you can say, where there is no scattering. They, like for example, clear water and shadows, right, which totally absorb and there is no reflectance, you can say. So if there is a small reflectance from a clear water, which ideally should have been 0, or a shadow, right? If there is a small reflectance, it is assumed that it is due to the haze, the scattering of light. So we have to identify such areas if they are present in your scene, clear water and shadows. And this value is assumed to be due to haze, and this value is subtracted from all the DN values of that. Now, second method which I told you, sun angle correction. It's a very known fact. The position of the sun relative to the earth changes depending upon the time of the day and the day of the year. Right? We know this, a very known fact. So in the sun elevation angle also, right, that is your time dependent, it is the location dependent, at which point on the earth you are. Right? Now the energy that is coming from sun, it changes, right, with the season. It changes with the season. That means basically the solar elevation angles are different, as I am showing here. The solar elevation angles are different. So the distance between the earth and sun is also different. So the amount of energy which is coming is also different. We know in northern hemisphere, the solar elevation angle is smaller in winter than in summer. Right? So, so the data which we are capturing in different solar elevation angles will cause different illumination effect, right? So you have to remove this solar difference, right? You have to assume as if the sun was overhead, right? Instead of at different angles, we can assume that the sun was at overhead. What would be the reflectance, right? So this elevation correction, the sun angle correction or elevation correction, it will remove your seasonal position illumination difference. Right? Now, why it is necessary? It is necessary when we are working with different data sets, we need to mosaic, or when we are using temporal data and we need to do monitoring change detection, right? So that those times I need to do this sun elevation or sun angle correction, right? So I'm saying that I need to remove the effect of solar elevation as if sun was totally above the overhead, right? So that angle is called as solar zenith angle. So the zenith angle is actually the 90 degrees minus the, this is, you can see 90 degrees, so this 90 degrees minus the solar elevation angle. So then how to do the sun angle correction? Now you see that I'm showing here two images. One in this image was captured with different sun angle. This image was captured with different sun angle. If I mosaic them, you can see they have different illumination. So if I remove the sun angles from both, in both the images, if I apply as if sun was overhead and then mosaic them in the resulting image, you are not able to make out if these were captured in two different times, right? So this is why we need to do the sun angle correction. So image data under different solar illuminations will be normalized by dividing the DN value of each image by the solar elevation angle for that particular time and that particular location of the image, right? So, or you can say cos of the zenith angle. DN value for this image divided by the DN value divided by the solar elevation angle, sine of the solar elevation angle, right? That would be the corrected image here, or DN value multiplied by the cos of the zenith angle, and anything would be the same. So for both the images, it needs to be done, and then you can move on. Okay, so this covers with the first error, which was radiometric error. Radiometric error, again I repeat, it is the DN value gets distorted. The DN value gets distorted. Now coming to the second component, which is geometric error. Geometric error means the shape of the pixel. The geometry of the pixel is distorted. So when we correct geometric position of a pixel, we make it conform to a regular size, to a certain map projection, to a certain scale. So that is geometric correction, right? Now, your image may have geometric error, may not have geometric error, but still the step called as image rectification would be necessary to remove this error. Now, one example I am showing here is that we know how the image is being captured. Let's see with the help of this animation. You can see the satellite is coming, it's capturing one line, and by the time it moves to the next line, you see the Earth rotation, right? So this, if you look at this, if the satellite is capturing this one line, by the time it comes to this next line, the Earth has rotated, right? And the Earth has rotated. So what you are getting image like this, whereas your each pixel should have been, each line should have been offsetted to the west, because you have Earth rotation effect, So you can see now in this animation, right? Now this is not an error, right? Because satellite also will be moving from north to south, line by line, capturing data. Earth also would be rotating beneath it, so that we get periodic coverage of the Earth also, right? So that means the north to south movement of the satellite, right? And Earth rotation, it will give you the complete data set for the Earth, right? But image is given to us is in this rectangular fashion, whereas each line should have been offsetted to the west, as shown here in the solid line. Right? So we need to fix this. We need to fix this Earth rotation effect. It's not an error, it's an effect, right? So we need to fix it by the step called as image rectification. Okay. Now, in addition, there can be many geometric errors also, like in whisk broom type of sensors, where the mirror is rotating, right? So the mirror scan velocity will be different, right? The corners would be larger, the center would be square, panoramic effects, and so on. So all those type of errors will be there in the image. Even if there is no error, if you have an image which is perfect without any distortion in the shape, you may want to overlay it over a topo sheet. That means the projection of the image and projection of your topo sheet may not match. Or you may want to overlay an image over another image. So you have to do this step called as image rectification or registration. So when you want to overlay your image over the topo sheet or another image, there are basically 4 differences in geometry which you need to get. The geometry, that means the image has its origin at top left corner. the topo sheet or the other image may have its origin in a different location than the imagery of your imagery under consideration. So that means you have to translate you have to shift the image so that it fits over the appropriate area. You may have to expand the image or compress it to fit over your topo sheet or another image, depending upon the resolution of the image and the scale of your topo sheet. Right? You may have to expand the image or compress the image. Then also it will not lie rectangular, you may have to rotate it. And the last difference, skew or shear, is offsetting of each line to the west because of that earth rotation effect. So these four differences in geometry we need to remove by a process called as rectification. So it's a process by which I can overlay one image over the other. I can overlay one image over the map. Right? So why it is necessary? It is necessary if I want to use my image as image map. I use a map to make accurate area, distance, direction measurements. So same thing when I want to use my image as image map. Now, these are two different grids. Image grid is in terms of rows and columns. Pixel values, pixel addresses in rows and columns. Your map, your topo sheet is in certain projection system, northing, eastings, or latitude, longitudes. That means grids which have two different coordinate systems, row column and latitude, longitude, or row column and northing, eastings. Right? So that means you have to transform the data from one grid. That means your image grid, which is in rows, columns, to your map grid, which may be latitude, longitude, which may be northing, easting, right? Depending upon which projection system which you are using. So this is done by grid transformation, that is by mathematically linking the image grid with the topo sheet. So this is an overview of how it is done. So this is basically it is done in two steps. First step is mathematical transformation, where we compute the geometric coefficients for mathematical equations that will be used. Okay? So the mathematical equations will be used between the image and the topo sheet. Right? So certain pixels will be identified in the image for which we know the map coordinates. Right? So these are called ground control points, and mathematical equations called polynomial equations will be used. The fitting will be done using the least square. Now, those of you who are not from the mathematics background, please do not worry. Right? It is a step which will be going on in the background. You only need to identify the ground control points. That means the points which can be identified on the ground and on your image, or points which can be identified accurately pinpointed on the image and the topo sheet. Right? Those are called as ground control points. And then the grid will be rotated and the DN values will be filled. The second step, which is called as intensity interpolation. So now let's see these steps one by one in detail. Okay, so we need ground control points to match the two. Which two? Image and topo sheet. So to match them, I need ground control points. So ground control points will be distinct points which can be very well identified on the image and on the topo sheet. Right? For example, a road intersection, a corner of a building, corner of a tower, and so on. So that means my ground control point will have two set of coordinates, and image coordinates, rows, columns, and map coordinates, latitude, longitude, or northing, eastings. Right? Now the accuracy of your transformation will depend upon the accuracy of your ground control points. So I need accurate ground control points. And ground control points should be well distributed over your entire image. Now, if you have very high resolution imagery, then you can find the road intersections. You can find corner of buildings, airport runways. Even marking on airport runways would not be visible. But if you have a smaller, low resolution, medium resolution imageries, you have to take larger features like urban area, larger urban area, or certain geological feature. Right? In those cases, we have to be very careful, as I have written here. Landmarks which can change over time. Please do not mark them as ground control points. Like for example, if you are taking corner of a lake, the lake water may have receded or may have expanded depending upon the season. Right? Similarly, you have a forest, tip of forest you are taking, and the forest may have been depleted, afforestation or deforestation, anything. Right? So the tip is changing. So don't take those points which can vary over time. And we require a large number of ground control points depending upon the type of mathematical equation that would be used. Okay. How many those minimum number are there? That also depends upon your equation. Now we can use a simple equation, polynomial equation, a first order polynomial equation. That means a simple polynomial equation instead of going to the complex polynomials. We can use a simple first order polynomial equation to make 4 changes in our geometry. So a first order polynomial would be sufficient. Now we have to solve this polynomial for our particular image and our particular topo sheet. So I need to calculate these constants by providing the ground control points. Now when I provide the ground control points, these equations will be solved using the least square polynomial fitting, and we will get these values for A0, A1, A2, B0, B1, B2. Right. So now to solve this equation, it's a simple first order polynomial. I need a minimum of 3 ground control points. These 3 ground control points will make my image fit over the topo sheet. But taking only 3 ground control points, I will not be able to check how much was my error. Right? With 3 ground control points, error will always be 0. So we need at least 1 more ground control point to check the error of transformation. And how to say my transformation is perfect or not is by a term called as root mean square error. Right? So accuracy is computed by computing the root mean square error for each ground control point. Now remember, I have 4 ground control points. 3 was minimum requirement, at least 1 more for accuracy. So for each ground control point, I calculate the RMS error. What is RMS error? Now see, when I solve this equation for my particular image, my small x and y is my image, capital XY is my map coordinates. I can do the reverse computation also. That means for input image where it would lie on the output map, and vice versa also can be computed. So I compute the RMS error for each ground control point by saying that my first pixel, the ground control point was this value, my computed value is here. So this distance between the two, this distance is my error. Right? And as you see, the smallest this distance, more accurate. Right? If the computed value is overlaying on the source ground control point, that means your RMS error is 0. Perfect situation. Right? But you know, perfect things do not happen, right? Because it's a fitting technique that we'll be using. So we will get some distance. That means my computed value would be little far from your reference ground control. And this distance is called as root mean square error. It's a Euclidean distance, you know, distance between 2 points, x1, y1, x2, y2. So you can take the distance, d is square root of x1 minus x2 square plus y1 minus y2 square. So distance, and the smaller the distance, the smaller the error. Okay. So that is our requirement. The error should be the smallest. Right. Now, acceptable, how much is the acceptable RMS? Acceptable RMS depends upon what we want to do with this rectification, right? What is the end use of the data? Which type of data being used? What was the accuracy of the ground control point? How you have collected the ground control point, whether from topo sheet, whether from GPS, differential GPS, right? Previous sessions. Right. So normally an RMS error of less than 1 per ground control point and an average RMS error of less than 0.5 is acceptable. So here you see I'm showing that we have taken 4 ground control points. These were the image coordinates and these were the latitude, longitudes or the northern eastings. For each ground point, the RMS error was computed. Now this RMS error should have been less than 1, which is this. And if I take average of this, it should be less than 0.5, which obviously it is. So with control points, able to calculate the forward equations and the backward equations. Forward equations means if an image pixel where it would lie on the map, and reverse equations, that means a map location where it would lie on the image. Both equations we need to compute. We don't need to compute, the software will compute it for us. We only need to give it for these coordinates, right? Identify the points. I will show you further. So once I've calculated both the set of coordinates, I have rectified my grid. If you remember the first step, I have rectified this grid in this animation. So they are overlaying over each other. Now the rectified grid needs to fill with the DN values. And that is my second step, which is intensity interpolation or resampling. Now in simple words, why I need to do resampling? When I'm overlaying one grid over the other, they will not match exactly. They will not match exactly. One grid, the grids will be rotated, matching in the rotated fashion. Right? So if my original grid was neatly in rows and columns, my output grid will not be matching to the input grid in neat fashion. And I need output grid to be filled with each DN value. So I look back where it came from. And when I look back, because of the fitting technique, my resulting line and column numbers are real and not integers as my original input image was. So when this occurs, we need to do interpolation. We need to do resampling. And the three general methods are nearest neighbor, bilinear, and cubic convolution. These generally used methods. So what you would actually do if your two grids are not matching, your first instinct would be to take the nearest pixel. Right? So that is my nearest neighbor approach. Right? So for example, if this square image which I am showing here is my corrected image grid, and the input image and the corrected image grids are not matching neatly, they are rotated. So for this pixel, if I want to fill a value, this one is the nearest pixel. Okay? This one is for this pixel, this is the nearest pixel. So similarly, if you talk in terms of quadrant, right? If the reference value is from here, this is the nearest value. So this pixel value will be taken and replaced. Like for example here, if the value that needs to be filled here is coming from a location called as 2.4 and 2.7. Now 2.4 doesn't exist in the input image. In the input image, it is either column 2 or column 3. It is either row 2 or row 3. There is no row as 2.7. So the nearest would be rounded up. So 2.4 will become 2, 2.7 will become 3. So 2, 3, the value is 15. That 15 value will be taken and placed here. So this is the nearest neighbor approach. This is the nearest neighbor approach. Right. The second method of resampling would be take the 4 nearest pixels. Take the 4 nearest pixels, find their weighted average. Not the simple average 9 plus 6 plus 15 plus 18 divided by 4. No, depending upon the distance of this pixel from each of this location, a weighted average would be computed. A weighted average would be computed, right? And the value will be replaced. Now, if you ask, why should I do this method and why not the first method? The advantage of, as I had in the previous slide, okay, the advantage of nearest neighbor method would be the output value is from one of your input value, right? So the data will use your original data. It's easier to compute and faster. There is a small disadvantage with this method, that some of the values from the input image will never find its value in the output image. So the image would look blocky. It will not be smooth. So if you use bilinear method, it will remove that effect. It will remove the effect of the smoothing. Right? Sorry, it will remove the effect of blocking, and it will smoothen the image. It will smoothen the image. There's certain disturbance. Some voice back is coming. So the next method is cubic convolution. Now, cubic convolution is similar to your bilinear interpolation. Here we take a weighted average of 16 nearest pixels. There is 16 nearest pixels. Advantage and disadvantage would be similar to your bilinear method. Advantage and disadvantage would be similar to your bilinear method. So this is what you would be actually doing if you are trying to register one image to another. So you would be marking the ground control point on the image and the topo sheet. You would mark 4 such ground control points, compute the RMS, and just a mouse click will make it rectified. So if this was my input image, marking those ground control points, right, you can see the image is rectified, oriented according to the north-south oriented map. Just few more slides to show you that I have taken 3 different data sets for the same area. The resolutions were different. One was 23.5 meter, one was 10 meter, one was 5.8 meter. That means my details go on increasing. Now these are 3 different satellites, 3 different sensors. I wanted to overlay them over one another. Now that means I need to do this step of rectification, even if there is no error in the image. Now once I do that, I find ground control points between the 2 images. And you see my RMS error here is only 0.47. And if you look at the individual RMS, it is less than 1, and average RMS error is less than 0.5. So this is acceptable. When I overlay, you can see my barrage of one image is overlaying over the barrage of the other. Only the resolutions are different, right? That is okay. But I intentionally introduced error. If you see, I intentionally introduced error here. I have so much error, average error. RMS error from, I only introduced error in my first ground control point. You see here, and the RMS error was coming in each of the ground control points. And when I do resampling, if you see these images are overlaid, but they are looking shifted, right? Because of the RMS error. Right? This was done intentionally to show you that if my RMS error is less than half a pixel, average RMS and RMS error less than 1 pixel, my images would be overlapping like here. And this is not at all a desired position. Right? So this covers the first component, that is image rectification and registration. So if I do the step, I will remove all the radiometric and geometric errors by using this step. Right? So now I am open for discussion. You can ask your questions